about the motivation of doing quantum field theory. Okay, and you know one more motivation which I have not told you, the fundamental interactions in nature. If you describe them, so field theory is the better way to do. Whether it is the classical field theory, let's say, if you are doing the gravity, okay, you do a classical field theory. I mean the Einstein's equations. Okay, so those are the kind of field equations. So that describes the structure of the space-time and how gravity emerges. Okay, and similarly, let's say if you are having an electrodynamic phenomena, you do by the Maxwell's equations. Okay, so E and B, they are the fields are A field, you know. Okay, electromagnetic field. You quantize it, you get the quantum electrodynamics. Okay, and similarly, if you are having, let's say, the strong interactions, okay, so you describe them by a suitable field. Clear? So this is how we do. Okay, this is you can think field theory is just a language. Okay, whether it is classical field theory or the quantum field theory, it just provides a language to understand the fundamental interactions in nature and the fundamental process or the process what are occurring in nature. Okay. Okay, let's try to attempt. We'll go through the historical development of the subject. Okay, so this is the suitable way so that you can understand better things. Let's try to develop a relativistic wave equation. Okay, if you are having a free particle, let's say, and you try to attempt to make a relativistic wave equation for that, like you are having for a non-relativistic free particle, you are having a for any non-relativistic particle bounded by a potential, in a potential or without a potential, you describe it by a Schrodinger equation, is it? So similarly, let's try to have a wave equation for a particle, okay, that moves at the relativistic speeds. That means we are trying to mix the quantum mechanics and the relativity to figure out what is a wave equation corresponding to that. After doing a wave equation, we will try to see what are the complications with that or what are the problems with those kind of wave equations. Okay, so this is how we will go through the course. Okay, before that, okay, let me revise the notation what we have done earlier. Okay, so we define the interval. So you are having, this is the definition of the interval. So if we are having two events separated by, let's say, you are having two events. Let's say you are having here C dt dx, or let's say C t x y and z. They are separated by the infinitesimal distance. That means it is ct plus c dt, something x plus dx, y plus dy, z plus dz. Okay, so defining the distance between the two events, we describe it by an interval. Okay, and this is an invariant quantity. Okay. So we are having now events. So we describe events by like this thing. If you are having this object greater than 0, if it's a positive quantity, what are those events called? Time-like events. Eh? So these are time limit-like events. Okay. If ds square is less than 0, so we describe them by space-like events. And if ds square is equal to 0, so those are light-like or null events. Eh? Okay. So this is already we have done in the previous semester. Okay. Is it visible? Okay, now we introduce a quantity. Let's say we'll introduce two types of vectors. So let's write that x mu as equal to ct x, y and z. Okay, and we define another quantity x mu as ct minus x minus minus y minus z, such that the length, okay, of the vector is given by, okay, how we define the length? X mu, x mu. Okay, so I'm assuming summation convention. Summation convention is sum over repeated index. Okay, so let me write. So mu goes from, let's say, 0 to 3. So using the summation convention, so it is the same thing. So I am using summation convention. Okay, so what is that equal to? It is simply equal to c square d square minus x square minus y square minus z square. So you can write this as c square d square minus, like this thing, x square plus y square plus z square. So this defines the length of a vector, of a special vector, is it? Okay, so let's write that. So you are in r square as x square plus y square plus z square. So that is simply r square. Clear? Okay, and in going from this vector to this vector, we define a quantity, a metric tensor kind of thing. So let's write it as eta mu nu. Okay, so like this, minus 1, 0, 0, 0. Okay, so let me do it this way. So if I have to define now the distance, let's say this ds square. So I can write it as like this thing, dx mu and dx mu. Will it? Okay, so this I can write as like this thing, eta mu nu dx mu dx mu. Okay, so you can now calculate this eta mu nu. So how much is that? Minus 1, 0, 0, 0, 0, 1, 0. Sorry, not minus. It's special. We are taking only the special components to be negative. Okay. Okay, we are taking the plus signature. Time we are taking the positive. Okay. So you can define the inverse of this thing. So eta mu nu. So that is the same thing. 1 minus 1 minus 1 minus 1. Okay. So these two are inverse. Let's say that what is the inverse of this thing? You just raise these two indices. This is the same thing what we have done previously. Okay. That's why I am going quickly to these definitions.
Minus 1, 1.
Yes.
Same as you write.
It will be the same thing because it's a diagonal matrix. What is the inverse of the diagonal matrix? It is the same thing. 1 divided by the element. Let's say if it is 1 divided, its inverse will be 1 divided by 1. Minus 1 divided by, sorry, 1 divided by minus 1. 1 divided by minus 1. Just the inverse of the elements. Okay. Let's say if it is, let's assume if it is A, B, C, D. So it will be 1 by A, 1 by B, 1 by C, 1 by D. Just so you need to inverse the diagonal elements. Clear? Okay. So you are having this kind of relation. If you are, let's say, this x mu nu, so you can write it eta mu nu x nu, and you can write this x mu as eta mu nu x nu. So you can go from a contravariant component to a covariant component, and you can go from a covariant component to contravariant component.
Is this mu as same as we wrote in previous semester matrix tensor?
So this is a matrix tensor. So I used G previously, but I am using here eta just to differentiate between the flat space. We are doing, I mean, the kind of theories on the flat space time. Okay, I am just differentiating a metric tensor on the flat space time with its counterpart in the curved space time. Okay, so we will generally write in curved space time G. Okay. Or a general kind of metric, we write G. So this is simply a standard notation. So here I am using, instead of G, I am using eta. Nothing more than that. Clear? Got it?
Yes.
Okay. So you can also, how much is that? So it is 1 by C, partial by partial T lambda. Okay. And similarly, you write this partial mu this way, partial by partial x mu. So that's equal to 1 by c partial by partial t and minus m. Okay? Clear? So this is the same thing. This is the notation what we have done. We have done actually in detail these kind of things. Clear? Okay. So now let's form a kind of operator from this thing. Okay. So these are all 4 vectors. So this is a 4 vector, this is a 4 vector. Okay, these are all 4 vectors. Okay. So if I write now like this thing, partial mu, so that is same as eta mu nu. Let's write partial mu, partial mu. Clear? So this is a kind of operator. How much is that? Anybody? So what is partial mu, partial mu? So let's operate these things on. Okay, so it's 1 by c square partial 2 partial t minus nabla dot nabla, so that is nabla square. So this is known as D'Alembert operator. Okay. So this is how we define it. It's a kind of, this is a Lorentz invariant quantity. Clear? Because if you see this is a scalar quantity, partial mu, it's a scalar quantity. Dot product between 2 vectors, that's a scalar quantity. It's a Lorentz scalar. It's a scalar under Lorentz transformation. Okay, now we can also define a momentum for vector p mu. Okay, so it is defined as E by C and vector p. Okay, so what is that equal to? E by C, so it is px, py and pz. Okay, so you can write now like this thing, p mu, it's lower component, so that means eta mu nu, p mu. Okay, so what is eta mu nu? So it is the the temporal component will remain the same, or the zero component will remain same. So it is E by C, and only the spatial components will change as sign. Clear? So you can form a invariant quantity p mu, that is same as what? P mu. So you can write it in terms of the eta tensor, this metric tensor. So p mu. How much is that equal to? So it is E square by C square minus P square. Okay, so this object is an invariant quantity. It's a Lorentz invariant quantity. Okay, so you can just use the Lorentz transformation to show that E square by C square minus P square is an invariant quantity. Clear? Got it? Okay. Okay, so we can also write these things. Okay. So now let's write this P mu x mu, this very objective. Okay. So dot, that means a dot product between P and x. Clear? But it is in the 4 space time. Okay, what is our P mu? So it is like this thing, P0 x0 plus P. Okay, so let me write here summation over I pi xi. Clear? Clear? So you know the definition of P, is it? What is P0? Tell me. So this lower P is 0. It is E by C. What is x0? X0 is upper. So that is Cp. Clear? Okay, plus, so that means it is the dot product between these two. Okay, so now let's write it. It's P1 x1 plus P2 x2 P3 x3. I should have put it in the first step. Okay, so this is equal to Et plus what is P1? So it is lower P1. What is that equal to? Minus Px. Clear? So what is this x1? It is simply x. What is P2? Minus Py. What is x2? It is simply y. Okay? Plus what is P3? Minus Pz. What is x3? It is z. Okay, so what that is equal to? Et minus Okay, minus is everywhere, so it is something like a vector p dot a vector x. Clear? Got it? So I will write this very object. Okay, so this is the notation. When I don't put a vector with the without a vector notation, I mean, and the capital letters. So this implies it's a 4 vector. Eh? This p dot x means p mu x mu, is it? If I put an arrow explicitly, it means it's a 3 vector. Eh? So this p, vector p is what? Px, py, and pz. So this is the notation. So you must remember it. Eh? X, y, z. So vector, when I put the vector notation or a vector overhead, it means it's a 3 vector. Eh? So it means you are dealing with the special components of a vector. Clear? When I don't put the vector notation, so p dot x, if I put it in this way, it means it's a 4 vector. Eh? Clear? So just remember this notation. Okay. Okay, so let's go to the Lorentz transformation. So this is all what we need, what we require. Any problem in this notation? Any problem? No. Okay. Okay. So let's review quickly Lorentz transformations. We will do Lorentz group in detail later on, but we'll simply, because we require these transformations. Okay? So what are Lorentz transformations we have done? So you start with a 4 vector. Okay? Let's say you are having a 4 vector. The components of the 4 vector are x mu. Okay? So you make a coordinate transformation from one frame to the another frame. Okay? Let's say you go from some k frame to k prime frame. Okay, the coordinates in this very frame are related to the coordinates in this frame in the following way. Okay, so let me write. So you are having, okay, let me write this way. So you are having this x prime mu. That means the coordinates in the primed frame. Okay, so they are related to the coordinates in. Let me write the coordinates in where? In the k frame. Okay, by this way. Clear? So where lambda mu nu is a transformation matrix. The way you are doing, okay, so let me revise briefly. So you are having x prime, if you, in the 2-dimensional space, okay, if you rotate your coordinate system, coordinates are related like this thing, plus y sine of theta, and y prime is equal to minus x of sine theta plus y cosine of theta. This we can write simply as x prime y prime. Okay, a matrix. What is that? Cosine of theta, sine of theta, minus sine of theta, cosine of theta, and x and y. In other words, you can write, let's say, your x prime is related by this matrix. Let's write that as lambda and x. Clear? Let's not put any I and j on this thing. So lambda represents this transformation matrix. Clear? Got it? Similarly, you will be having in general a 4x4 matrix. Okay? Clear? Got it? Okay. So we'll figure out in case of Lorentz boosters this lambda mu nu is. Okay. So let's write in case of Lorentz boosters. So you know, okay, so x0, you remember this thing? X0 prime goes as, anybody? Okay, so let me write this thing. X0, x1, x2 prime, x3 prime. Okay, so these components go as this way, gamma, minus beta gamma, 0, 0, minus beta gamma, gamma, 0, 0, 0, 0, 1, 0, 0, 0, 0, 1, okay, x0, x1, x2, x3. Clear? So what is beta? It's V by C. And what is gamma? 1 divided by root of So these are the Lorentz boosts, and this will represent your lambda. Clear? Got it? Okay, so now let's check what is lambda 0, 0. Okay, so you can say this very object, okay, mu you can say it's a row index, and nu you can think as a column index. Clear? So now let's say, so this very object will be what? Lambda 0, 0. What this object will be? Lambda 0, 1. So this is lambda 0, 3, and so on. Clear? So what this will be? Lambda 1, 0. What this is? Lambda 1, 1, and so on. Clear? Okay? Okay. So now let's. Okay, so this lambda mu nu, so this contains in general. So this lambda contains in general boosts plus rotations. So you are having rotations of the coordinate system. Okay, you can be having rotation in, let's say, xy plane, yz plane, or in all the three space. Okay, you can be having boost like that. So you boost a particle, let's say, along x direction. So that is simply thinking. So you are rotating actually your coordinate system in tx plane. Let's say if you consider this kind, so here in this kind of transformation, you are boosting a particle along x direction. Is it? Particle is moving with some velocity v along x direction. Clear? There is no velocity along y and z direction. You can think now this kind of boost as a rotation in xt plane. Clear? So let's say if you are having a boost along, let's say x, y, z direction, that means arbitrary velocity in three directions. So you can think that also as the rotation in the entire space-time. Clear? In all space, spatial, and time components. Clear? You got my point? Okay. So now under these kind of transformations, so the length of the vector remains constant. Remains invariant. So length does not change. Let's say what is the length? So under these transformations, length remains invariant. So length is an invariant quantity. So what does that mean? That means x prime mu. Let's say x prime mu, that is same as what? X mu and x mu. So this is the length in the primate coordinates, and this is the length in unprimate coordinates. This remains same. Okay, so because if you look at simply the two-dimensional coordinate system, calculate the length of the vector. So the length of the vector is invariant, it's a scalar quantity. It's invariant under any kind of transformation. Clear? Okay. So now let's check. So what are the conditions that are satisfied by this lambda? Okay. Okay. So now let's take this thing. So you are having x prime mu. So can I write this as eta mu nu x prime mu and x prime nu? Can I write it? To make both as the contravariant components. Clear? So because I know the transformation between, so a contravariant component goes this way. Huh? So you can be having similar the covariant, then it will be inverse. Huh? Clear? Okay. So you are writing like this, eta mu nu. What is x prime mu? So I will write lambda mu. Let's write lambda x lambda. Clear? Now what is x prime nu? So you write lambda. What is the index here? Nu. So let's write sigma. So it is x sigma. Clear? Everybody followed it? So let me repeat again. So you are having x prime mu. So x prime mu, it goes as lambda. Put a lambda and x. Clear? Okay, so what is the index here? You put it here, and then put another index at the bottom and put it here, because I am making a transformation from the same type of components to itself. Clear? Got it? So you are having this as a contravariant and a contravariant here. Clear? So in other words, you can put an index here, put a lambda and x, put one index here, another index here. The index what you put here, you put it that here, contract it. It's simply the matrix multiplication. Okay. So what is that equal to? Eta mu nu lambda mu lambda. Okay. Then I will put lambda nu sigma and x lambda x sigma. Clear? Okay, by definition, this is equal to, okay, this is equal to what? X mu, X mu. Is that true? Invariance property, yeah? Because length is invariant, okay? Definition of clear? So how much is that equal to? So let me put as it as x lambda. Let's write x lambda because it's a dummy variable. Huh? Can I write it? Everybody? Okay. So this I can write, let's say eta lambda sigma x lambda x sigma to match this very object. Huh? Clear? Because both are same. Huh? Got it?
Yes, sir.
You got it? So that's why I have put it in this way. So then put eta lambda sigma to have this thing. I will now compare the coefficients. So because this object is same as this object, it means the coefficient here has to be same as this thing. Clear? So what it means? So it means eta mu nu lambda mu lambda. Okay, lambda nu sigma, that is same as lambda. So what it gives me? So it means this lambda mu nu multiplied by lambda mu nu is equal to identity. Clear? Is it? Is it clear? Okay, so now let's write. Okay, you can contract. So let's contract this mu. So nu will come here, is it? So you will be having lambda nu lambda. Then lambda nu sigma is equal to what? Eta lambda sigma. So eta is actually what? The diagonal matrix. Is that true? With minus one, okay, 1 minus 1 minus 1 minus 1. So if I see, okay, so let me write it. So it is something, let me write it. So it is lambda contract. So mu will get contracted, nu will come here, nu lambda, then you are having like this thing, nu sigma. So that is what? Eta lambda sigma. Clear? Got it? So if you raise one of the indices, let's say if I raise, let me put nu here, put a lambda here. So raise this index like this. So what that is? Eta lambda sigma. Clear? So because lambda is a free index, lambda appears here, lambda appears here. It's a free index. If I raise this one, I need to raise this one as well. Is this equation clear? Is this equation clear? Okay, good. So what does it mean? So what is eta lambda sigma? It's actually an identity matrix, delta, Kronecker delta. Is that true?
Yes, sir.
Okay, so look here. So you are having eta mu nu. Now look here. So it is 1 minus 1 minus 1 minus 1. Is it? So if I write now eta mu nu. So what I am doing actually? Let's check these elements. It will be eta 0. Okay. Eta 0 0. Raising or lowering the time component does not change the sign, is it? So it will be 1 here. Now let's write eta. Okay, what is eta 1 1? It's minus 1. If I lower now 1, eta 1 1, what it yield me? A change in sign. So what it will be? 1 here. Clear? So it will be 1 1 1 1. What that is actually equal to? Delta mu nu. So it's a Kronecker delta. Clear? So much more? And the Kronecker delta is the representation of an identity matrix. It's a matrix representation of an identity matrix. Clear? Because it represents an identity matrix, Kronecker delta. So in other words, I can say, so you are having some lambda, okay, so that's actually equal to identity, is it? So it means when you are having A multiplied by B is equal to identity, it means A is inverse of B or B is inverse of A, okay? So we call this as lambda inverse. So this object is lambda inverse. So this is your lambda and this is equal to identity. Clear? Got it? So much more? So that means the transformation matrix, what we have written in Lorentz transformation, it's an invertible matrix. Clear? So it is having an inverse, and the inverse of that matrix, okay? So let me write lambda nu. Okay. So let me write lambda mu nu. Okay. So its inverse is same as lambda. So
Lambda sigma.
okay. Now tell me. So it is simply mu nu. It is just the interchanging of columns, rows and columns. Okay. You change rows and columns, it will be like this thing. Clear? So that's why I have put this index here. So I have put it here and this here. Eh? Clear? Got it? Okay? So this is simply just the definition of the inverse. Nothing more than that. Okay? So what is important? Important quantity what we have arrived at? So this very quantity. Okay? So when, okay, let's say lambda is a real matrix. Let's assume this lambda is a real matrix. So you are having some matrix O multiplied by its inverse is equal to identity. What we call them?
Invertible.
Huh?
Invertible.
Yes, they are invertible. These are there is a well-known name for them. Orthogonal matrices. So O transpose is equal to identity is equal to what? Let's say if you are having, you know unitary matrix very well. Let's say you are having a unitary matrix U dagger is equal to identity, is it? So that means the inverse of a U you calculate by simply dagger, is it? So you are having, let's say U dagger is equal to identity. So that means if you know U, calculate its dagger. So it means it's an inverse to what?
U.
So is that same thing? So it means we can calculate the inverse of this matrix just by dagger. Huh? Similarly, if you are having a matrix, so this is the, let's say if you are having a real matrix, okay, then you are having O transpose is equal to identity. That means this has to be inverse of this thing. Clear?
Yes,
So it means you can calculate the inverse of an orthogonal matrix just by calculating its transpose. Clear? Similarly is here. So that's why I am doing this thing. If you are having a matrix here, and if you say this is the inverse, okay, so it must be the transpose of this thing. So just interchanging the rows and columns just by and with a sign change, because temporal components and spatial components, they change differently when you raise or lower the indices. Clear? Got it? Okay. Okay, now let's take the infinitesimal Lorentz transformation. So these were the finite things, now the general cases. So let's take infinitesimal Lorentz transformation. So what does that mean? Let's take infinitesimal rotations. What does that mean? So you rotate your coordinate system in an infinitesimal step. Clear? In a small increments. If you have to figure out, because these are the continuous transformations. Clear? So the continuous transformation you can have infinitesimal steps. Let's say if you are rotating about the circle. Clear? So you take a radius vector at some point and then change it in the small steps. Is it? Ultimately you will get a full rotation. Clear? So it's a kind of continuous transformation. Theta is varying continuously from 0 to 2 pi. Clear? Similarly, let's understand these infinitesimal transformation. What does it mean? So you are having this lambda. Okay, so let's take this lambda mu nu. This is a transformation matrix. If I write it a small element, okay, infinitesimal, this small change, okay, how much is that? Let's say if you are having a matrix and you approximate it by some infinitesimal matrix. So how I can write it?
Big matrix plus epsilon.
Huh? Yes?
Something जो हमारी actual matrix है वो plus हम epsilon.
Okay, let's say if you are having yes, Somebody? Yes, you.
एक्चुअल मैट्रिक्स प्लस हम एप्सिलॉन करते हैं स्मॉल.
No, not the actual matrix. Let's say I have to take the infinitesimal value of some variable x. What does that mean? Eh? Let's say x varies continuously from, let's assume from 0 to 1, or let's say 1 to 2. Clear? And I need to take the infinitesimal amount of x.
Delta x.
Huh? So it's proportional to epsilon, is it? The change is proportional to epsilon, is it? Clear? So now if I am having a matrix, what I should write? So this matrix should be actually proportional to how much? The small quantity, is it? Some identity matrix, let's write eta mu nu plus some small change. Let me write omega mu nu. Okay, so this is the infinitesimal matrix. So since this is a matrix, you approximate it with the identity. So eta mu nu is essentially identity, is it? Except those minus and pluses, is it? Plus some what? Small change, the epsilon amount. Clear? So look here, if I have to rotate in an infinitesimal steps, clear? So what does it mean? It means you are adding to the identity some small step. Let's say you start from this very point, okay, and you have to move this way. Let's say you have to move on this very circle, and I have to put an infinitesimal change, okay. So this small angle d theta, clear? Clear? So what it essentially means? It essentially means doing nothing. That means the identity plus the epsilon amount. Clear? So suppose if let's say if this is a rotation, so let's write this as r. So it will be some identity plus some epsilon amount, let's say theta, through an angle theta. Clear? So you start with a baseline and put some epsilon amount. Then again the epsilon amount, is it? Then again the epsilon amount until you reach a finite value. Clear? Clear? Okay. So now let's figure out what are the consequences of this. We don't know what is the nature of this omega mu nu for the time being. We only know this eta mu nu is a symmetric tensor. Is it? So this I forgot. Eta mu nu is same as what? Beta mu nu. So it's a symmetric metric tensor. Okay, and we don't know what are the properties of this thing. And we will calculate it in a moment for our Lorentz boosters along its direction. Clear? Okay. So what is our identity? We have just written. Okay. So what was that? So let's write eta mu. So what was? So I have put lambda. Huh? Huh?
Mu.
Eta mu. So lambda mu. Then what
sigma.
was the index here?
Sigma.
No. Just
First was mu lambda, then was mu sigma.
It is lambda, then lambda. What is it? So first was mu.
Yes, sir.
Okay, then
Mu
it is
sigma.
mu sigma. So it's eta lambda. I will use the same notation what I have done in the lecture. Okay? Clear? Okay. So this is our identity. Now let's substitute this lambda in this way, please. Okay. So what is our? So let's write LHS. So how much is that? So it is eta mu nu, and then you are in lambda. Lambda is what? Lambda mu nu. So it will be mu lambda plus omega mu lambda. Clear? So then you are having lambda nu sigma. So it is eta nu sigma plus omega nu sigma. Clear? Clear? Okay. So how much is that equal to? Eta mu nu. So let's multiply it. So it is eta mu nu lambda, then eta nu sigma plus eta mu lambda omega nu sigma plus Okay, eta nu sigma. Okay, let me put this here. Omega mu lambda for your purpose, nu sigma plus, then you are having omega mu lambda, omega nu sigma. If you see this, like, since omega is a small quantity, it is an infinitesimal quantity, this is actually order of omega squared. Clear? We can ignore it. Got it? Okay, we can ignore these terms. So that means I can put it approximately equal to eta mu nu. Okay. So let me write it as eta mu lambda, eta nu sigma plus, then you are having eta mu nu, eta mu lambda, omega nu sigma plus eta mu nu, eta nu sigma, omega mu lambda. And we are ignoring the order of omega square terms. Clear? So now tell me what this is. So anybody? So you can. So you will be having eta mu lambda. Okay. Eta mu lambda. So this nu gets contracted. Then you are having eta mu sigma. Okay. So or you can contract this nu. So nu will come here. There is no. I have contracted this nu. So nu will come down because nu and nu gets contracted. Nu will come here. Okay. Got it? Plus, so what it results, mu and nu gets contracted, nu lambda, omega nu sigma plus nu and nu gets contracted, mu sigma, omega mu lambda. Clear? So now mu gets contracted, what it gives me? So lambda will come here, lambda sigma plus, so now look here, so you contract nu, so it will come, lambda will come down, so lambda sigma plus, so mu will come down, omega sigma lambda. Clear? Clear? Everybody followed it? Okay. Huh? Followed it? So anybody has any confusion here? I'm going slowly for you people. Okay. Okay, so now what this is equal to? What this is equal to? So it's equal to, okay, or I will write this as equation first, from equation first, so I will write eta lambda sigma plus omega lambda sigma plus omega sigma lambda, that's equal to eta lambda sigma. Clear? So this object I have shown that, and that's equal to eta lambda sigma. Now this object cancels with this object. What you got? No? Okay, yes. You get this identity. Omega lambda sigma plus omega sigma lambda, that's equal to, it implies omega lambda sigma, it is equal to minus omega sigma lambda. So it means this infinitesimal quantity which I am adding to the eta, it has to be antisymmetric in nature. Clear? Got it? So it means it's an antisymmetric tensor. Antisymmetric rank 2 tensor. Okay, now how many independent components you are having for an antisymmetric tensor? Okay, so the first thing is, okay, so let me write the diagonal elements of this omega mu nu. So let's say omega mu nu, its diagonal elements are what? 0. If you are having an antisymmetric matrix, okay, its diagonal elements are always 0. So that means, so omega mu nu has 0, 0, 0, 0. These are the diagonal elements. Clear? Got it? So I should put this way. So this omega is then, okay, let's write omega mu nu for the diagonal. So what about this thing? So it will be omega 0, 1, omega 0, 2, omega 0, 3. What about this thing? Omega 1, 0, omega 1, 3, 1, 2, 1, 2, omega 1, 3. Then omega 2, 0. Okay, so 2, 0, omega 2, 1, omega 2, 2, 3. Then omega 3, 0, omega 3, 1, omega 3, 2. Now look here. Since this is antisymmetry, so omega 0 1 is same as minus omega 0 1, is it? So that means these are the same things, sir. So I will write omega 0 1, this is minus omega 0 2 minus omega 0 0 1, right? Okay, minus omega 0 3. So what this will be? Minus omega 1 2. What this about? Minus omega 1 3 minus omega 2 3. Clear? So that means these upper diagonal elements and lower diagonal elements are same. Clear? Just with a sign change. Eh? So now tell me how many independent parameters are there? How many independent elements? Only 6. So that means you are having 6 independent elements of omega mu nu or parameters. You can write this as parameters as well. Okay, now what it corresponds to? We'll get the interpretation. Now let's take the Lorentz group in general. Okay, so you can think Lorentz group as, these Lorentz transformations, I will just call it as for the time being Lorentz transformations. So you can think Lorentz transformation in this way. So you can take a boost along x direction and independent way, a boost along y direction and boost along z direction, is it? So all these three boosts can be done independently, is it? So how many ways you can do the boosters? 3 ways. And you can be doing rotations, let's say in xy plane. You can be doing rotation in yz plane or in zx plane. So all the 3 rotations are independent. Clear? So that means this Lorentz transformation will be generated by 6 independent parameters. Clear? 3 boosters and 3 rotations. Clear? So those are actually here. I mean, although in complete lambda mu nu, but since I am considering the infinitesimal Lorentz transformation, you can think, let's say, these terms, the parameters corresponding to the boosters, let's say along x direction, along y direction, along z direction, and these will be simply the rotations along x, y, y, z, and zx. Clear? Got it? Okay, so we will see actually when I talk about the Lorentz group in detail, then you will see what is the significance of these parameters. Clear? Got it? Okay, so now let's take an example. Let's try to figure out this omega mu nu in the simplest of the cases and check whether it is really antisymmetric or not. Okay? Okay, so you are having the Lorentz transformation along x direction. So I will consider only x and t directions. Clear? Because y and z remain the same, they do not change. So it means, so I am having like this thing, x0 prime and x1 prime. So that's equal to, so gamma minus beta gamma minus beta gamma and gamma. So that's equal to x0 and x0. Clear? So now this is the complete boost, is it? So now let's take the infinitesimal change. Clear? So what does that mean? So let's take this, what this object is. Our lambda mu nu is here what? Gamma minus beta gamma minus beta gamma and gamma. Just remember, so this transformation matrix is like this thing. One index up, one index down. So if you lower down one index or you raise the other index, so these elements will change accordingly. Clear? Got it? Okay, now let's take the infinitesimal change. Clear? So what does that mean? So if I take, let's say, beta is very less than 1. So what it means? V by C is very less than 1. Okay, so what will happen to gamma? So it implies gamma tends to 1. Clear? Because gamma is what? Gamma is equal to root of 1 by V square by C square. So this tends to 1 because this is very small. Okay? So now let's write this objective. So this object is then, so I will write it as 1 minus beta and 1. Clear? So how I will write it as 1 0 0 1. Clear? And then you are having minus, okay, so let me put plus 0 minus beta and 0. So you can think this as what? The identity matrix plus an infinitesimal quantity. So now tell me what this matrix is. Okay, so you write this simply as delta mu nu. Clear? Clear?
Yes, sir.
Okay, so what this is? Omega mu nu. Now which omega mu nu? So antisymmetric properties are defined when both indices are lower or both indices are up. Clear? So for a mixed tensor, you can't define it. So now let's check it. Okay. So what is your omega mu nu? So that's equal to 0 minus beta and 0. Now let's calculate. Okay, so let's write this as, so it is equal to omega 0 0, omega 0 1, omega 1 0, omega 1 1. So how much is that equal to? Now let's write, or I will write for you people, omega mu nu. Okay, so you are lowering down what? Mu index. Clear? So let's lower down this index. So it will be omega 0 0. So 0 down, so it is 0 1. So 1 will down. So now I am lowering down what? 0, is it? Clear? So 0 lowering down will not change the sign. So here I am lowering down 1. It will be minus 1 0 and omega 1. So that means what you are having. So if you now look at omega 0 1 and omega, so it is minus time. So it means your omega 0 1 is equal to minus beta and omega 1 0 is equal to beta. Is this the antisymmetric now? Is this the antisymmetric? Okay, so you can write it. Okay, so you write it like this thing. Omega mu nu. So that is simply equal to, okay, 0 will remain same. Okay, now look here. When I am putting omega 0 1, so that is same. Okay, now you are having 1 here. So it is minus, so it will be plus beta and 0. Clear? So is this an antisymmetric matrix? Clear? Huh? Everybody followed it? Huh? So you need to first look at this very matrix. Okay, then put either this up or this down. Huh? Clear? So what we will do? So I have put it in this way to show you more generally. So you will be having, so this is omega 0 0 0 0. Okay. Clear? So and so on. Huh? Okay, so let's stop here.